Is there anything to copper being, there we go, being used? Turns out, yes, actually.
They don't like copper making the staff and breaking down.
So it does, once you flush down your drains, there's a reason we switched away from copper pipes for the outflow, especially. For your sewer pipes and for your gray water, we switched away from copper pipes because some things like copper are like strong acids and things like that can cause the copper to break down. But we still use copper. I guess we've switched over to PEX. Is the most modern thing, but which is those like red and blue.
Sorry.
No, it's okay. But there's an issue with copper in drinking water in general because copper does bioaccumulate and is slightly neurotoxic. So it's not great for you, but that's not metallic copper. And for the most part, copper is pretty inert when it's exposed to water. In fact, if anything, it is actually helpful. They actually like copper when you're doing distilling because it'll actually react with any sulfur that's present. And sulfur in drinking water was a problem, especially in like hot springs and stuff like that. Copper will make copper sulfide, which is super insoluble if you expose it to sulfur. So it'll actually remove sulfur from stuff. So it does purify a little bit. Metallic copper, if you take metallic copper and elemental sulfur, they will actually, it'll oxidize the copper and reduce the sulfur, and you'll wind up getting copper sulfide. But most things, copper is pretty inert when you expose it to that. So copper actually is pretty good for pipes, and they actually, I don't know if they knew what they were doing. My guess is that if you just use like stone as like a catch basin or for drinking water and stuff like that, a lot of minerals are slightly soluble in water. So my guess is that they realized that they were getting different taste in the water if it sat in the stone versus putting it in copper or just drinking it, you know, when it first fell. As it sat in the stone, it would change the taste. And copper actually does have some antimicrobial properties too. So it'll actually keep things from growing in your water, which is was always a problem when your predominant source of water was open to the air.
Yeah.
So there's something to it. It's not as good as more modern materials like PVC or PEX. My father-in-law's building a house right now and did most of his own plumbing. And they use, now it's just like these little tubes that are either red or blue, depending on if it's hot water or cold water, or if they're black, if it's the outflow. And they're easier to work with than traditional PVC. The problem with all of these plastics is that any organics are going to get into the plastics or dissolve them. So like you never want to flush acetone down your drain at home because you're going to wind up dissolving your pipes. And so it's a different issue. If you had copper for your outflow, you can't use like acid-based drain cleaners or you'll dissolve your pipes. But the acid-based drain cleaners are fine in PVC. So it's more about knowing what you have and then cleaning it and dealing with it appropriately to keep it from falling apart. So depends on what. So Drano, there's two different forms of Drano. There's the crystal form, and I'm using Drano as a catch-all for most drain cleaners. I want to say that Drano traditionally, the brand was a crystal. It's sodium hydroxide, basically. So basically, you just dump that down your drain, add a little bit of hot water to start dissolving. It'll actually break down hair, skin cells, things like that. All that gunk that winds up in your drains gets cleaned pretty well, but it'll also break down metal pipes. So you don't use that if you have metal pipes. And the other one, the liquid drain cleaners, are acid-based. They're just basically sulfuric acid. Sulfuric acid will react with metals as well and break them down, more so even than the hydroxide. So when in doubt, the most safe drain cleaner to use for your pipes is the crystalline kind because it's just sodium hydroxide, and most metals won't react with sodium hydroxide. They'll react in acidic conditions.
Yeah.
But never use anything organic because if you do have any plastic pipes, you basically are just dissolving them. So, good question. Let's talk about rules to differentiate between anti and non-aromatic, because we talked about. All right, so these top three, I think I have them for these top three are the ones that everybody got right. Maybe I got them out of order. But if we're just counting lone pairs, 1, 2, 3, 4, 5, so it's an odd number, and it's a cycle.
Yeah.
With no, and everything's fully conjugated. So that tells us this one's aromatic. Same idea here. Pi bonds, one lone pair. So a total of 3 pairs of electrons, odd number makes it aromatic. Pi bond, one lone pair, and another lone pair is a total of 4. So still a cycle. It's still conjugated all the way around. So that makes this one anti. So our criteria, to go back to Taylor's question, what is our criteria for anti? Anti-aromatic means it has all the same criteria as aromatic, except with an even number of electrons. And our criteria for oh, that's what happened. I copied and pasted the same one twice. So there's one missing on here. Let's see which one I grabbed wrong. I missed. That one, got that one. Ah, this one is one we do want to see. All right, so
It's not columns 2 and 3, it's that,
it's specifically which of the two.
it's specifically that it follows all except the number of.
Correct. Correct. So odd versus even differentiates between anti-aromatic and aromatic. Non-aromatic means it's missing one of the first two criteria. It's either not conjugated all the way around the ring or it's not a cycle. So 3 pairs of electrons in this one. That's not a lone pair.
Right.
It's missing a lone pair, which means this is Sp2, right? Just like the rest of these. Can this positive charge resonate around the whole ring? Yeah, because we could move that pair over here and then that would put a positive charge there, right? And so on and so forth.
Yeah.
So is it conjugated it is a ring, obviously. Is it conjugated all the way around the ring? Yes. And does it have an odd number of electron pairs? Yes. So it's aromatic. It sounds weird because we've been talking about aromatic as being, oh, these things are all like ridiculously stable. But then I show you an example that has a charge, and we're used to thinking of charges as being unstable. This is a case where this particular carbocation is way more stable than any other carbocation should be because it gets that aromaticity. What's going on with the eraser here?
Sorry, but the non still follows the last rule of having an odd number.
Non So if we put our three rules, so it's got to be a cycle and it's got to be conjugated all the way around. If either of those is false, then it's non-aromatic. And then once you get the next criteria is that Foucault's rule, is it has to be an odd number.
And it has to follow that rule
To be aromatic.
to be non-aromatic.
To be non-aromatic, one of these can't be true.
But the bottom one is still true, or?
It might be, it might not be. It doesn't even matter. Because as soon as one of these is false, the flow chart falls apart. I see your question, sorry. It's irrelevant because we kind of go in this order. First, check that it's a cycle. 2, check that it's conjugated. 3, check that it's an odd, the number of pairs. If 1 or 2 falls, it's non-aromatic. And if you have 1 and 2, but it's an even number, then it's an anti-aromatic. So with that in mind, what are these last two? Take a second. Obviously, they're both cycles, right? Is the first one, the middle one, is it conjugated all the way around?
So the lone pair on the edge,
Mm-hmm.
it already has like 3 tubes on top of this, so the lone pair can't repeat, right?
Right. I think more importantly than the 3, this nitrogen already has a pi bond as part of the ring structure. So yes, this lone pair is not going to be part of that. But these two are conjugated. Is it conjugated all the way around the ring though?
I don't know. Like, I feel like it is, but I also feel like it isn't.
There's only 2 in what's the hybridization on this carbon?
Oh, they wouldn't be able to go up there because the carbon's already full.
The carbon's already full. The carbon's already sp3. sp3 carbons can't participate in resonance.
Right.
Right. So sp3 oxygens can participate in resonance because they have the lone pair. And sp3 carbon has no lone pair, and it has no room to accept electrons. So it doesn't have electrons it can give, and it doesn't have a way to accept electrons. So an sp3 carbon as part of your ring automatically is not conjugated.
So it's non-aromatic.
Non-aromatic. Same thing, right? It's not conjugated, so it's non-aromatic. We spent so much time on Thursday focusing on the lone pairs for oxygens and nitrogens that I forgot to go back and remind you how carbons work.
Yeah, I forgot to not have to tell.
Yeah. All right. Questions on the quiz questions? Yeah, all those settled.
Yes.
Okay. Let's talk about some reactions. So we're going to do reactions. We're going to spread them out a little bit. We're going to talk about a couple of oxidation reactions, or an oxidation reaction and a reduction reaction, in a fair bit of detail today. And then we're going to talk about NMR and IR organics. So we'll do another practice. We'll end with, like we started with on Thursday. And then next on this Thursday, we're going to talk about substitution reactions of aromatics, but that's kind of its own. Some of the concepts carry over, but I don't want to overwhelm you with too many mechanisms all at once. So we're going to spread it out a little bit. So if we're trying to oxidize things, this is one of our most common, well, historically, ways that we could oxidize things. Do you remember why we were trying to move away from?
Because chromium
Because chromium is really toxic.
is really novel.
It leaches into groundwater really easily, causes birth defects and cancers, all sorts of bad stuff. So we don't really want to use it, but it's still what, you know, our textbook example of here's the easiest way to oxidize something. It doesn't oxidize everything though, because if you try to put it with benzene, nothing happens. And if we put it with just an alkane, nothing happens. We've seen this reaction so far as if we have an alcohol and we put it with the dichromate, Cr2O7, with the acid, etc., we turn it into a carboxylic acid, right? The other reaction that can happen is if you have an alkane to benzene ring, that actually kind of gives it a bit of a handle. So it made it kind of, we didn't spend a ton of time on the mechanism for this one because when metals are involved, there's odd numbers of electrons, it gets kind of tricky. Well, we basically said we had to have an oxygen, we had to have a functional group in order for the reaction to happen. A benzene ring is a functional group that's not reactive itself, but it creates that sort of handle that it can react with. So what you will see, if you put a strong oxidizing agent, potassium permanganate is another fairly strong one. It's not strong enough to do this reaction, so we haven't seen it yet. But potassium permanganate or chromic acid will oxidize the benzylic carbon. Remember, the benzylic is similar to allylic. Remember, allylic means adjacent to a pi bond. So benzylic is adjacent to a benzene. It's not part of the benzene ring. It's one carbon away because we get extra, it gets special treatment. I was going to put two L's in there. The benzylic carbon gets special resonance, but it's not protected by the aromaticity. So that allows it to react differently than the benzene carbons themselves, phenyl carbons, or just alkanes. Right? And interestingly, this only works if there's a hydrogen on the benzylic carbon. Which is weird because when it's done reacting, there's no hydrogen left. So there's something about the hydrogen on that benzylic carbon that allows the reaction to happen. Either we can pull the hydrogen off, or there has to be something about that hydrogen being adjacent to the benzene ring that allows this to happen. Because if we have a tertiary carbon, or a quaternary carbon rather, in the benzylic position, nothing happens. Right, so easy enough. Benzylic carbon that has hydrogen gets turned into an acid group. It's always the same product, basically. So let's try it.
I'm doing, is it K and then over on top, and then H to zero over on bottom?
No, either. So it could be, and the other way we could write it, remember that our dichromate was just a way to make the chromic acid. So we can also write it as Na2Cr2O7 in H2SO4.
Yeah.
So you can write it like that. You can write it just as KMNO4, and occasionally you'll just see it written as chromic acid, H2CrO4.
Okay.
Right, those are all strong oxidizing conditions. So they will all oxidize that benzylic carbon.
What is it add?
What is what?
What does it change to the carbon?
So it takes the benzylic carbon, as long as there's a hydrogen,
Yeah.
and turns it all the way to a carboxylic acid. So the toluene here would get turned into benzoic acid.
For B, there's two. Would be to both.
Yep. As long as they both have a hydrogen.
Right.
And that's one of the weird things about this is basically
Yeah,
the other carbon disappears as far as we're concerned. It's one of those really strong oxidizing conditions. It probably gets turned into CO2 or some other small carbon molecule, carbon dioxide maybe even. But as far as we're concerned, it just disappears.
But for synthesis, it's good to know.
Yeah, it's a good way to lop off chunks of your molecule.
Yeah. I'm thinking now they're up for.
Wow. So, what's the name of this molecule?
Is it? That benzoic acid.
It's benzoic acid. How do we name this one?
Benzoic diacid.
It's good guess. I believe that the way that we would actually, so that this is another one where it's got a common name. if we're naming this as a prefix, we're modifying benzoic acid. I think we'd call it carboxybenzoic acid. Is the prefix for a carboxylic acid group is carboxy. So similar to methoxy or something like that. So we could say it's carboxy benzoic acid. Then we just need to specify where one of them is. So that's part of 1, 2. So that'd be 3 carboxy benzoic acid.
Okay.
This is also one with its common name. And actually, one of the first weird common names that you learned back in Gen Chem, what was the first indicator we used? First time you did the titration in Gen Chem. Anybody remember? What color did it turn? Pink. It was phenolphthalein.
I would have guessed that 100 years.
So now you know that what phenol means.
Yeah.
This PHTH actually means,
2.
so this is actually phthalates.
Okay. You don't include saying like the benzene or anything, like benzoic phthalic acid?
No, because phthalic acid is two acid groups attached to it.
Okay.
Let I see it. There's one out there. And so we would say this is either 3 phthalic acid, or say if it's not adjacent, it's 1 removed. What do we call that?
A little bit. No, it's like the.
Start with an meta.
Orthometa para. Or those 2 metas, 1 para is twice. Use something. Oh, or those 2 are.
So you could write this similar to cis versus trans, as would say C or a T, or orthometa para, sometimes you see M. Or you could write out meta.
Also, like meta, like the company.
Yeah.
Why are they called meta?
So meta means, and its most basic, meta means self-referencing.
Okay.
So like meta humor is humor that's aware, like if like Deadpool is an example of meta humor because he's aware he's in a movie and talks like breaking the 4th screen is an example of meta humor. So I think that the reason that they went meta was because they were pushing that whole that VR world thing. They called it the metaverse, right? But it's not the real world, it's 1 step removed from the real world. It references the real world, but it's not the real world. So I'm guessing that's where Zuckerberg got that idea. Meta humor used to be a big topic of discussion with hipsters, like liking something ironically is an example of meta humor. You like it, you don't really like it, but you say you like it, but is that really being a fan of something? Yes, exactly. I've used a little too much water for its own matter. One of my favorite examples of meta humor is I'm so meta, even this acronym. Because what is the acronym?
I'm so meta.
I'm so meta, even this acronym is meta. Because the acronym, the sentence is referencing itself, that makes it meta. Right, so in this instance, meta just means once removed, but it's kind of tied back to that same root.
Sorry, Bobby. Hey, what's up? What do I see the project from the lab?
Yes. You know where they are?
Yeah.
Here, come on in here.
Thank you.
There you go. Just make sure it's locked and bring it back to me. All right. And then, so then what would we name this last one over here? I think Kathy tried to wash these. We still don't erase very well.
She might have, she can get in the wood.
Well, we have to indoctrinate her into the Swiffer, the cult of the Swiffer.
She tried it a couple times last week. Wait, we did just the last bit.
We didn't name the last one, but I cleared room because this one's bigger. Still would be phthalic acid, right? It still would be meta.
Still met with acid, then it would be say as the common.
As the, actually, I think that's probably the IUPAC name as well. But this doesn't follow our standard rules.
Or church.
And so this is the case where M really, we probably don't want to use M because we have a tri-substituted benzene. So, and we could call that a T-butyl group, tert-butyl group. We could also say, call those 1,3 phthalic acid, call that 1, that 3, it would be 4. If we're using the parentheses instead of calling it a T-butyl group.
We would say.
Thank you. Thank you. No worries.
Try.
What's our longest continuous carbon chain that starts counting here? If I did that, it would be a methyl ethyl group, right? Adding another methyl group to a methyl ethyl would be dimethyl ethyl. So using the parentheses, a dimethyl ethyl group is a T-butyl group. And a methyl ethyl is an isopropyl group.
And we don't just write to people.
You could also write 4-T-butyl 1,3 phthalic acid. Would be just as good as the name.
So.
I would tend to go this way. Just because I like the parentheses more than memorizing the common names. And if I build this in MolView, so actually MolView says the IUPAC name is 4-T-butyl benzene 1,3-dicarboxylic acid. I don't like that at all. That's what MolView says. I don't like it either, but you've got that. You can say benzene 1,3-dicarboxylic acid instead of phthalic acid. All right, so the reaction's pretty straightforward though. If you've got hydrogen on a benzylic carbon, it gets oxidized all the way to a carboxylic acid. So this is actually another way of now adding a functional group to something that was just hydrocarbons, right? So before, if it was just a pure alkane, the only way we had to add a functional group was radical bromination.
Right.
This gives us one more way, as long as part of it is benzene, right? Because once we get to a carboxylic acid, then we can reduce it, turn it to an alcohol, make it a better leaving group, et cetera, et cetera. Although if that was our end goal, I don't know why we would just use NBS and just put a bromine there, because bromines are mostly fair work, but it gives us something we can do. So just to recap, this is like 3 chapters worth of reactions as they relate to benzene.
What's the O?
O just means oxidize. You can see an O in brackets, that means we're gonna oxidize it, so that could mean any of those 3. Potassium permanganate, sodium dichromate, or chromic acid could all fall under that umbrella. What specific oxidizing agent you're gonna use is just gonna depend on what your stopper looks like. All right, and once we add a bromine, so in the way we would do our radical bromination. Right, we always do NBS and Y. It's less important that you do NBS when it's bromine, because if we just did bromine, so the reason we used NBS, if you remember going back to it, is if we had an allylic position, if we just did Br2, and like we get 2 competing reactions, right? If we do it with the light, we get a bromine added here, but we also wind up with the possibility of making this, right? And breaking the pi bond. And NBS is the way that we could avoid that, because it kept our concentration of bromine much lower. So less of an issue here, because we're not going to, even a radical reaction, it's not going to really readily break up a benzene ring, but out of habit, we should probably still call it NBS. Right, the only time that this oxidation doesn't work is if we don't have hydrogen. And so you can see also why that idea of treating synthesis kind of like a subway map kind of makes sense, because if we get on the train here and we're trying to go up here, then we have to kind of navigate our way around. How are we going to do that? But it's all about finding which pathways work that don't take you to a dead end. We wouldn't want to do this, because we can then do that and do a reduction.
But it's
you know, it's not as good of an idea. It's not part of our map.
Yeah. Yes.
This one looks
Yeah.
a little bit better now. All right. When it comes to reduction benzene, we've talked about this a little bit already. We can do a reduction by just doing a high straight hydrogenation. You can take benzene and 3 equivalents of hydrogen gas and turn it all the way to cyclohexane. And it's even downhill in energy. But the activation energy is such that in order for this to happen at a reasonable rate, it's got to be catalyzed. You have to be 100 atmospheres at 150 Celsius. Less than ideal. for Earth-like conditions. Trying to think of what the pressure is on Venus. Might be something you could do on Venus because Venus is both hot and has very high pressure, but I don't think Venus has. You'd have to get out to the gas giants to get a naturally occurring pressure in 100 atmospheres range.
Well, we just crumble though, like, there's no way to be able to withstand.
Yeah, basically. So it's either 12, every 12 feet or every 20 feet you go underwater is approximately 1 atmosphere of pressure at. So to get to 100 atmospheres of pressure, we would have to go down 100 plus or 100 times 12. So 1,200 feet. So this would be like being 1,000 feet underwater. So yes, we would just crash.
Yeah.
In theory, our body is actually very resilient. If we just went straight from sea level to 100 atmosphere, just be crushed. Our body is actually really good though at adapting to different pressures with scuba suits. The whole reason that scuba works is because by continuously breathing and being exposed to that pressure gradually, you actually can withstand pretty high pressures. I don't think that you can scuba dive anywhere close to 1,000 feet though.
Yeah.
I want to say that the record is something like 500 feet. And even that requires switching tanks because what will happen is you wind up dissolving too much gas in your bloodstream if you go to that high of a pressure. So you have to switch to a tank that has no nitrogen, where it's just oxygen, and I think they use helium.
Oh, that's great.
So yeah, and because helium is so inert and doesn't cause any sort of health effects when it's dissolved in your bloodstream, you still have to be really careful coming back up.
Yeah.
So that you don't get the bends, but I believe you can go down at least 200 feet. I want to say that you can get closer to 500 feet. But I'll check that at a break because I'm kind of curious now. Either of you ever scuba dive? It's fun.
I believe you.
If you like fish, and you like swimming.
Love the ocean. I love fish and I love aquariums, but I'm scared of being in it. I like to watch from a distance. I've snorkeled.
Snorkeling's fun.
Yeah, I've did not want to do it with me in Hawaii. No, I didn't do it in Hawaii the first time. I did it after I graduated my senior year of high school.
You know what you could try that's a little bit easier to get into is they do this thing called snuba, where basically instead of carrying a tank on your back, you have a long line that's attached to a generator that sits on the top that pumps air. So if the air source floats and then you have got like a 20 feet, then you can basically, it's like snorkeling, except you can go down about 20 feet and stay there pretty much as long as you want.
That's cool.
So it's kind of halfway in between. It's fun. My family's always done all sorts of water sports, so my whole family is scuba certified, although we haven't been in a very long time.
Have the kids been?
The kids have not been. So when I say my family, I meant before kids.
Yes.
So Laura and I are scuba certified. My parents and my brother and his wife were all scuba certified. But we haven't been since people started getting pregnant because it's a whole different thing.
Yeah.
I think you can. But it was one of those things that when Laura was pregnant, she didn't want to take the risk.
Yeah.
Because it is a non-zero, it's like skydiving. Yes, it's safe until it's not.
Yeah.
And so she said, well, I'm just not going to do it when I'm pregnant. And then it turned into, well, now we have a baby, so I'm not going to do it when we have a baby.
Yeah.
Now we have children and we have to be responsible and things like that. So I know. All right. Couple things before we take our break. So with nickel, 100 atmospheres of hydrogen and high temperatures, we can go all the way to cyclohexane. But it also means that if we have normal hydrogenation conditions, platinum, 2 atmospheres of pressure at room temperature, we can hydrogenate an alkene without touching the benzene. So for the most part, benzene rings are going to be, I don't want to say inert, but they're so much less reactive. That as long as we keep standard reaction conditions, we can mostly do anything we want to an alkene without worrying about the aromatic's own category of functional group. And so if we actually want to break the aromaticity, we have to get a little bit more creative. And the way we do that is with a reaction called the Birch reduction. And the Birch reduction looks somewhat similar to our dissolving metal reaction. Because remember, our dissolving metal reaction, we had ammonia and sodium metal. This still requires sodium metal and ammonia. It's just we do it in methanol instead of in straight ammonia. And the net result is kind of interesting. You wind up taking your benzene ring with 3 conjugated pi bonds, and you turn it into something that's no longer conjugated. All right, so you take 2 carbons on opposite sides of the ring, and you turn them both into sp3 carbons. So now our conjugation is completely broken by this. And our mechanism for this looks a lot like that dissolving metal reaction as well. So one of the things about sodium and a lot of the metals, one of the reasons the metal reactions get really tricky is because they can give away odd numbers of electrons. So sodium is really, really good at giving away an electron, but it only has 1 electron to give at a time. And the fact that it's giving away 1 electron at a time means we're talking about a free radical reaction. So this is one of our first reactions that we've seen that's a combination. It's a free radical step mixed with a regular step. So this is tricky. So sodium gives away a single electron to a carbon. And that carbon breaks a pi bond so that we get a carbanion and lone pair on a carbon. And then on the opposite side of the ring, we have a radical. So this is a radical anion. And on one half of the molecule, radical on the other side. It's weird. Well, once we have a carbon with a lone pair, though, that's a pretty strong base. And so then the methanol that we have floating around just has a proton source. So we go from being a radical anion to just radical. And once we have a radical, that radical is going to go out and find something else that has an electron, right? So since we still have, as long as we pay attention to our stoichiometry, we still have more sodium atoms around. So we've got another source of a single electron. So the radical just turns into being a lone pair. So the most unstable step is this first step. And it's trickiest to draw too.
Yes.
It's a lot of these single barbed arrows. But then once we get here, like, oh, well, obviously that's going to grab a proton. And then once you have a single radical, it's going to grab another electron from sodium. We get another lone pair, another anion. Which is then, once again, just going to act as a base and steal a proton from methanol. So the net result of a Birch reduction is going to be an isolated diene. So this is, if you just look at the before and after, oh, we hydrogenated it. But it's the way that we hydrogenate it that creates this isolated diene, which now is just going to act like an alkene. So basically, this is a more reasonable way to take a benzene and break the aerobic system. And then we can do whatever we want. All right, let's take a break. We'll come back and we'll go through that one more time to kind of solidify it. And then we'll start doing practice and talk about some finer details of predicting the products. So let's go back at 5 after.
Okay. And then I go with Facebook, see what happens. I keep waiting for bring a Starbucks back. I want first like little search and catch with them. I was in the days. I didn't take a break. It's the hard one. Just somewhere else. No, and then the whole scene through and that was fine. Well, you forgot these to the mom from yesterday. But she's already on.
We have a little bit left.
Okay, practice.
It's gonna sit, we're gonna practice. Thing we have to talk about is when it's just benzene, this is really straightforward. You have the same product every time. Because you start with the reactant every time. If it's a substituted benzene, then that makes things a little bit trickier. Because where do we put the sp3 carbons versus the sp2 carbons if it's substituted? And so the most important thing with benzenes when it comes to figuring out where stuff is going to go, this is the part that's going to come back later, is that we're going to talk about electron donating versus electron withdrawing groups. So similar, we've used those terms before, we're going to fully define it now. But basically, if you have an electron donating group, and electron donating groups are anything, any alkane group, and anything with a lone pair. Except that there's a gray area. Because electron withdrawing, the number one way that you can see electron withdrawing is if there's a pi bond conjugated to the benzene, it's electron withdrawing. And if it's really electronegative.
It's a carbon in the other
Correct.
Okay.
So anytime you've got a nitrogen in the allylic position or an oxygen in the allylic position, it's electron donating. If you put a fluorine in the benzylic position, it's electron withdrawing, even though it has a lone pair. So our gray area is just the halogens. Fluorine, chlorine, and bromine attached to a benzene ring they're electron withdrawing because they're electronegative, but they're also electron donating because they have lone pairs. So those kind of counteract each other, and it winds up being, it depends on what the exact situation is to some extent. All right, so But before we get into that, the more obvious cases. If you have an electron donating group, the carbon that the electron donating group is attached to is not going to be the reduced spot. Because think about what the mechanism looked like. The hydrogens or the carbons that get reduced have a lone pair on them with a negative charge. So anything electron donating, you've got more electrons pushing in against the lone pair. Electrons repel other electrons. So you're not going to put this lone pair on the carbon that has an electron donating group. And conversely, if you have an electron withdrawing, we can spread that negative charge out more. So electron withdrawing groups are going to make it easier to reduce that carbon. And I'm going to
No, the electron withdrawing group may reduce that.
correct. Right, so electron withdrawing winds up being more important because it makes it easier for the reaction to happen. Electron donating makes it harder for the Birch reaction to happen because our first step is give electrons to a benzene ring. If there's an extra electron density, it's harder to force an extra electron. So for the Birch reduction, and I'm going to be very careful how I say this because it flips next lecture.
Okay.
For the Birch reduction, electron withdrawing substituents activate the reaction. They make the reaction go faster. And for the Birch reduction, electron donating groups deactivate and make it go slower.
The electron donating group makes it so.
Correct. Because it's harder to force an extra electron into the benzene if it already has an extra electron density.
Wait, so for Birch reduction, the electron withdrawing substituents activate the what?
We call it, basically it speeds up the reaction. We call that activating the reaction because it makes it speed up.
Like then.
Yeah, so we call this an electron withdrawing group is an activating group for a Birch reaction. Don't get too hung up on that terminology because when we talk about substituted benzenes and we talk about activating groups and deactivating groups, we're usually talking about it flipped. Because our next reaction that we're going to spend all of the next lecture on is electrophilic substitution. Electrophilic substitutions is going to get flipped because they're attracted to the extra electron density. Right, so for the Birch reduction, we have a list of possible substituents. electron donating at the top. And then all the way down to the most electron withdrawing at the bottom.
Nope. That's these. Okay, so, but also there's the faster is activating group. Does the slower have a name?
Deactivate. We're using that terminology. Although I'm actually second guessing you've been using that terminology here because I don't want to confuse you for next lecture. Because that's the most standard. Yeah, but so electron donating means slower Birch production.
The middle part thing, like. What is that?
That's our gray area.
Oh,
So let's think about it. Our unstable intermediate looked like this, and we can either have our electron donating group here, or here. So when we're talking about whether this one's going to be electron donating or electron withdrawing, we really want to talk about it in terms of, is it going to stabilize our most unstable intermediate? Is there any way that a chlorine could make this negative charge more stable? I mean, there's a little bit electron withdrawing because it's electronegative.
but it's on the tertiary.
It's on a tertiary carbon. Well, not really tertiary because the chlorine doesn't count.
Okay.
So basically what I'm going to tell you is, because this is a gray area, I'm not going to ask you about halogens for the Birch reaction. For the sake of the Birch production, the halogens are considered electron donating.
And we only will be asked about the halogens in the gray area.
Correct. So for the Birch reduction, it will ask you about halogens. But it's a really common functional group, so I wanted to talk about it. So let's do some practice. So remember our number one criteria here was if it's got a lone pair or it's an alkane, it's electron donating. If it's got a double bond, it's electron withdrawing. And electron withdrawing means that your sp3 carbons wind up right next to your electron withdrawing group. Electron donating means that your electron donating group is attached to an sp2 carbon as well at the end. So what's our product for A? This is electron donating. Which means this stays on an sp3 or sp2 carbon. Right, we're not going to put an electron donating group on an sp3 carbon. So that means for A, our final product looks like that. It's B, C, and D. As for any of them where you have multiple substituents, you want to try and satisfy both of the criteria. They're both electron donating, they both need to be on an sp2 carbon. If there's a way to do that. There's possible ways to draw some of these isomers up so that you can't satisfy both of them. But usually there's a way, if there's only two of them, there's usually a way to make them both satisfy.
So like C doing the same thing where they're like parallel to each other on both sides.
They're always going to be parallel to each other. It's just a matter of how parallel in which orientation. It's gonna, but if we could draw everything the same. You science club people getting in the way of my whiteboard. So it's a good poster. That also works, right?
You guys. Back circle. Yeah, just draw them on your own. You don't need it to be perfect. Perfect. Yeah.
So what do we have to do for this one?
Keep that one where it is. And then move one of the other ones across from it.
Yeah. So E, that's electron withdrawing, right? So electron donating means it needs to be attached to one of the carbons that still has a pi bond. So for an electron withdrawing group, we need to attach to one of the carbons that's Sp3 that doesn't have a pi bond.
And when you say we need to attach, like we're attaching.
Well, really, we're putting where we're putting the pi, not we're attaching that. Because all of the sigma bonds are still staying the same. So we're not actually moving any of the carbons around.
And how do you keep some of this drawings? Because it had other things on it.
Because it's not pi bonds conjugated with the benzene ring. So for the last one, for F, we've got one electron donating and one electron withdrawing.
So we're gonna leave the one that has like one to the right. And then put the other one there.
So we need this one of our sp3 carbons has to be this one, right?
But I thought it could, right? Because of the,
Because it's electron withdrawing.
yeah,
So electron withdrawing means that that's the carbon that gets reduced. So this is the carbon that does not have a pi bond.
right.
Okay, so if that carbon doesn't have a pi bond, where do we put our pi bonds?
I mean, I agree with you.
Did I miss here what you said? Okay,
Yeah. And then parallel.
yes.
Okay. Wait, I thought it was finding it. This. Me every time we get in work. I know, I look at it and I'm like, never mind, I mean, it's this, then we didn't. I know, but at least I grind up.
All right, so it's possible to draw one of these where you can't satisfy everything.
Yeah, so we prioritize for satisfaction.
So generally speaking, if it's a case where you can only satisfy one thing, what's gonna take precedence is usually the activator. Because the activator works by lowering the transition state energy, right? So putting an electron withdrawing group on the carbon that's getting reduced is more important than where we're putting the electron donating group. Because the electron donating group makes it harder for the reaction to happen. But the electron withdrawing group makes it easier, and it's typically more important. That's it. I'm gonna try not to ask you questions that will ask you to split hairs like that, at least for the Birch reduction, because what's more important is the reaction that's coming up on Thursday. That's the one that's more likely to show up on a standardized test for moving forward, because it's a lot more universal of a reaction. This is kind of a niche reaction because this only happens when we have a benzene ring and we want to reduce it, and it's got in that are which one matters more only happens for a small subset of those reactions, right? So really, we can dive down into it in a lot of depth, but it's not really going to come up that often. All right, we have 15 minutes left. Let's talk about spectroscopy real quick. So when we're looking at aromatics, especially benzenes, there are a few things that tend to show up that help us determine if we have an aromatic region. And one of the ways that that can show up is, so for starters, we always going to have these CH bonds unless we have a benzene that's so completely substituted. So we'll see something in that region just above 3,000. But that doesn't allow us to differentiate between alkenes, right? Because alkenes will show up in the same spot. One of the things that do show up is these repetitive peaks in an area where we don't see peaks. So 1700 is where we would see our carbonyls show up, right? That's one of our go-tos to look at. But just above 1700 in this area where we normally don't see anything, you get what are called combination bands or overtones. And one of the things that's distinct about these is there are going to be several of them, and they're going to be all the same distance apart. They're not super strong, but they're somewhat uniform. So the size, the intensity of the peak is not the same for all these, but the fact that they're almost the same distance apart is our giveaway there. Because then these stretching and ring vibrations, now we're starting to fall into the fingerprint region. These are harder to tell, and they're not always this intense. And we never really want to get into anything down below 1500.
Yeah.
So those ones are harder to tell. But if you don't have a carbonyl, but you do have a couple big peaks right around between 15 and 1600, that maybe. There's a lot of things that can show up there though. But those overtones, they don't always show up, but when you see those, that's pretty much a dead giveaway that you got an aromatic. All right, and so when we talk about NMR, we already know that proton NMR, these are pretty easy to find, right? They're always between 6.5 and 8.5. They're always going to have a pretty large integration, unless we happen to have something that's a tri-substituted benzene. We're always going to have an integration for the whole thing that's 4 or 5. So, and sometimes the splitting, usually we just gotta mess stuff down there. It's hard to tell the splitting, with 2 exceptions. If it's a di-substituted benzene and it's symmetrical and para, we're only going to get a singlet. Because if these 2 substituents are the same and they're directly opposite of each other, that means that all of your hydrogens are identical. So if all of your hydrogens are identical, you only get a singlet. Because it's really all one signal.
Right.
If they're para and they're opposite and they're not the same, then you really only have 2 types of hydrogens. In this case, the red and the blue, which means you wind up seeing 2 doublets. Now, those aren't always going to show up this cleanly, because sometimes if X and Y are really close to the same amount of electron withdrawing, but not identical to each other, you can wind up with your 2 doublets on top of each other. Then it still turns back into a VMS. But occasionally you get lucky, you get something that looks like nice and clean like this. And that'll tell you what your substitution looks like. Because this where things are substituted on a benzene ring is one of the trickiest things about proton NMR. Because you get something like this, what are you going to do with that?
Yeah.
Luckily, in this case, it's 5 integration, which means we don't need to worry about that. Right, because there's only one thing attached. So you're lucky enough to be able to see the individual signals, and this this is applying to carbon 13 NMR, counting the number of signals in the aromatic region will tell you what the substitution looks like. So just like with proton NMR, where we said, okay, well, if they're identical and they're paired up relative to each other, we're only going to get one type of hydrogen. So we just see a singlet. If for the carbon NMR, that means that you only have 2 types of carbons. So if we're looking at our carbon 13 NMR, our aromatic region is between 110 to 175. Counting the number of signals in that region can tell you what the substitution is. Okay, because if it's paired up and they're identical, you only get 2 signals in that region. If they're identical in their ortho to each other, you get 3 signals. If it's di-substituted and X and Y are not the same, we're going to get 4 signals. But we also get 4 signals if it's mono-substituted. No matter what X is, if you only have one thing attached to the benzene ring, you're going to get 4 different carbons. So if we have an IR, a proton NMR, and a carbon NMR, how can we distinguish between these 2?
The top one and the bottom.
These 2, yeah.
The substituents are different than the box and
Well, but these should still show up in different spots too.
well, like the X and the Y would have their own bases.
Well, it depends on what X file.
Okay.
But one thing we can tell, this is a big mess, right? How did we know we didn't need to worry about substitution?
Because it said that.
Set 5. So how can we tell the difference between these 2?
What the integration is.
This will have an integration of 4 and this will have an integration of 5 on the proton end.
Right.
So how can we tell the difference between these 2? These are both going to have integration of 4. They're both going to give you 4 signals in the carbon NMR.
But what am I has X plus X Y? So does that mean those?
So basically, we look at the carbon, the proton NMR to tell what X and Y are. And if they're not the same substituents, then we can tell it that way. Exactly. Okay, so this is just another way of thinking. We've done carbon NMR, we've done proton NMR, we've kind of thought about some of this before, but this is the way we can think about it. This is just another way of thinking about it that allows us to kind of narrow in on things, because the substitution is one of the trickiest things to figure out when it comes down to it, right? If you have an X and a Y in their ortho, you get 6 signals.
What just makes me think of like, no, of like, roughly like developments, always like, because that's like a orthopedic term. Yeah.
Fun fact, the prefix ortho does not mean bones.
What does it mean?
I don't know, but osteo means bones.
Okay.
Maybe it also means both. I think it has to do with joints. So orthodontics is resetting your teeth better in their sockets.
Yeah.
And orthopedic surgeons focus on joints, not just the bones necessarily. But I don't know that. Maybe they came from the same root. They both have bones. Who knows? I'll look it up later. All right, so if we have X and Y and they're different in their ortho, we're going to get 6 signals. If we have X and Y and they're different in their meta, we're going to get 6 signals. So, and these are both going to have the same integration on the proton NMR. And they're both going to have 4 distinct hydrogens as well. So basically, these are the 2 cases where it's really hard to just look at the NMRs to figure out what their substitution is. Everything else, every other possibility for a disubstituted benzene, we can either use splitting, integration, or the number of signals to figure out what the substitution is. So let's try one real quick. We've got C9H10O. Do we have an aromatic?
I think so, because of the chaos right before some.
Yeah, 7. They're a little bit harder to see. 1, 2, 3, though. Those are our overtones.
Okay.
And then they don't look as clean because we've got a carbonyl peak right next to them, so they kind of get swamped by the carbonyl peak a little bit. But you can still see them. So we can be pretty certain, especially from the proton NMR, we've got that.
Yeah.
Is it monosubstituted, disubstituted?
But it's because of the chaos right before some and the speed things there.
Those 3 right there are those overtones. Let me go back to show you the clean one. In a really clean IR spectrum that doesn't have a carbonyl group, you might see them that neatly. They're not always going to be that neatly, but they're always going to be kind of weak in that same region where nothing else really shows up in roughly the same distance apart from each other.
But that can also be ignited.
Could be. Do we have anything else that indicates that we might have a carbonyl? What shows up all the way down like hey, there's some front. Okay.
Carbon double bond oxygen. With an H.
So an aldehyde potentially? It's less than 10 carboxylic acids show up more like 11 to 12. There's another reason you can't get carboxylic acid though. We only have 1 oxygen. So almost certainly an aldehyde which should match up with something on the carbon NMR, because carbon NMR, aldehyde and ketones show up between maybe 190 to 220. So probably that one right there.
Why is the carbon and the Mars so stacked?
Because there's a lot fewer carbon 13s. Because remember, it's only about like 1% of the carbons are carbon 13s, right? So we actually don't get as clean of a signal as almost all of our protons, RH plus, will show up in the proton anymore, which is why splitting works. We don't see splitting and we see more noise because we just have fewer carbons that are actually going to show up.
So 140.7 would be an aromatic.
Yeah, aromatic rings show up anywhere from like 110 to 170. So they could all be aromatic rings, right? If I go back a slide. We had 4 signals in the aromatic region, right? So which of these makes the most sense?
The one next.
And why?
One.
We only have 1 oxygen,
And that's fine.
and we have an integration of 5. And as long as we're looking at this and looking for more evidence that we have an aldehyde, we don't really need more evidence because we have a whole bunch of things to say aldehyde. That one right there, remember aldehyde carbon hydrogens show up on their own lower than all the other carbon hydrogen bonds. So that's an indication.
Aldehyde is, yeah, good.
That's the one that's weird that shows up all by itself. So we've got a carbonyl, we've got this weird peak by itself lower than everything else, and then we've got both of these. All of that says aldehyde. So what could we do? How could we draw an aldehyde that also has a benzene ring?
We have a lot of carbons.
We have a lot of carbons. How many carbons are in the benzene ring?
6.
So then we have 3 more carbons, one of which is an aldehyde carbon. Right, that's the one shown up down here.
Yeah.
Which means we've got 2 carbons left. Aldehyde has to go at the end, right?
Yeah.
And it's not disubstituted benzene. So if it's not disubstituted benzene, this probably makes the most sense, right? Does that also make sense with the splitting that we see in the proton?
Yeah.
Integration of 2, triplets, so 2 nearest neighbors and 2 nearest neighbors. Integration of 2 nearest neighbors. Integration of 2, 3 nearest neighbors technically, but remember that aldehyde one is not going to couple.
Yeah.
Because it's so different in energy. Right, so we didn't really add that much by talking about splitting patterns of aromatics. We've already been doing that. It just kind of formalized it a little bit, gives us, okay, it gives us a table we can reference if we wanted to. In fact, maybe I'll take this and put it in the white space right here.
That'd be nice.
So we have all of our carbon and our stuff on the same page. All right. We went 5 minutes over, so we'll start lab a couple minutes late. Give you time to go do your other stuff since it's Tuesday after all. Go to Senate, do all that. We'll make green yard reagents, and then next week we'll use them.